All right, so here we go. This is exam 2 review on functions, and we're going to start with a mathematical modeling problem. And so here we have the yearly enrollment in E in millions of students at universities and colleges in America as a function of the years T since 1965. So here's our table right here. So part 1 said use the table to answer the following problems. So here's our table. We have time. Remember, if it's 10, it's really 1975, 20, 1985, and so on. And then we have the enrollment over here, which is in millions of students. So 5.921 is really 5,921,000 students. Okay, so we want to use the average rate of change to estimate the number of students enrolled in 1988. So in 1988, first we have to figure out what t is equal to. So it's like figuring out your birthday if you were born in 1965. So 5 gets me to 70, and then 10 gets me to 80, and then 8 more gets me to 1988. So that's 23. And we go to look in our table, and what you notice is there's not an entry for 23, but you know that 23 is somewhere between 20 and 30. And so the idea is we can use the average rate of change. We can basically use these two data points to figure out or to estimate the population or the student population in 1988. So let's use some functional notation. So the enrollment E of 23, so the enrollment 23 years after 1965 is approximately, and the idea is pretty simple. You're going to look right here at the value for after 20 years, which is 12.247, which remember represents 12,247,000 students. So that's a good estimate, but we know it's a little bit more because 23 is a little bit bigger than 20. So what we do is we compute this average rate of change, which is the change in the output divided by the change in the input. So it tells you basically how many millions of students are changing per year on average. So on top, you're going to put 14.261. Remember, it's always the final minus the initial, and then minus 12.247. So that's the change in the student enrollment. And then divided by the change in the years, so 30 minus 20. And so again, this is going to be millions of students per year, and then you're going to multiply that by the change in years. So you're going from 20 to 23, and so you'll multiply that by 3. And so take out your calculator, and let's do this. So you put in 12.247, that's where we started, plus, remember you have to put parentheses around the top. So left parenthesis, 14.261 minus 12.247 in parentheses, and then divided by, now if you put 30 minus 20 in the bottom, you have to put parentheses around it, but that's just the number 10. So I'm just going to be divided by 10, and then multiply that by 3, hit enter, and out pops my answer, 12.8512. Now, I'm going to round this to 3 decimal places because all my outputs are rounded to 3 decimal places. So when I put this in, it's going to be, what? It's going to be approximately, so I just read this off my calculator, 12.851. All right, since the 4th decimal place is a 2, you just round down, and so you get 12.851. And of course, you should probably put what it represents. It says it's millions, 12.851 million students. So that's my answer. Okay, so let's do the next one. So on the next one, it says use the average rate of change again to estimate the number of students that will be enrolled in 2010. So in 2010, let's erase this over here. We have to figure out our t value. So for our t value, we have t equal to what? Well, it starts again in 1965, and we have to go to 2010. So 35 gets us to 2000, then 10, so this must be 45 years. And when we look at our table, we have the same sort of issue. It doesn't fall in our table, it actually falls outside of our table, so 45 is down here. And so to figure this one out, we can use functional notation again, so E of 45. And notice how I won't write equals, I'll write approximately because we're approximating this value. And so what am I going to do? Well, this is a good approximation, the best one I can get from the table, basically, from the entry in the table, so 17.488. But I know it's probably larger because you can see the numbers seem to be increasing. So what you're going to do is, again, you're going to add the average rate of change. And now the average rate of change for this one, which two data points are you going to use? And so I'm going to use these two right here because it's the closest to what's happening outside of the table. So here you just take the difference in the output, 17.488 minus 14.261. So that's the millions of students, a change in the students, and so it's in millions, remember. And then the change in the input, which is 40 minus 30. And that's year stuff. So you're going to get millions of students per year. That's how they're changing on average. And you'll multiply by 5. And again, we'll put this into our calculator. So what do I have? I have 17.488. And then plus, left parenthesis, 17.488 minus 14.261. In parenthesis, divided by 10 again, because 40 minus 30 is 10. And then we'll multiply by 5. And remember, the reason we multiply by 5 is because we're going from 40 to 45. So we're going 5 years into the future there. And you'll hit enter, and out will pop our answer of 19.1015. And I'm going to round this to 2 decimal places. So what do I get? I get this to be approximately 19.102 million students. So that would be my estimation using the average rate of change. This idea of average rate of change is really sort of an obvious idea. Remember, if you graph these points, if these are your inputs and these are your outputs, and you put dots on a graph, basically they're going to look, something like this. And then all you're doing is basically connecting the dots. So you're connecting the dots, you're connecting the dots, you're connecting the dots, you're connecting the dots. And this average rate of change you're finding is the slope of each of these little line segments. And that's the idea. Okay, let's look at the next problem below this. So below this, instead of giving you a table, they're going to give us a formula. So it says use the formula now to answer the following problem. So notice I skipped a graph because we're going to do a graph in a minute. But I wanted to do a formula problem. So here's my formula, E of t. Again, this represents the enrollment in millions of students, and t is the time after 1965. And then this is equal to 7.111 times 1.024 to the t. And it says, the first question, how many students were in college in 1983? So the first thing is to figure out your t value. And again, I just use it as a birth date. So it's like 5 gets me to 70, 10 gets me to 80, and 3 gets me to 1983. So this should be 18. And I want to plug 18 into my function. So this is an input question. And so I want to find E of 18. And now because it's a formula, I can write equals. This says equals this. And so wherever I see a t, I'm going to put an 18. So I just have 7.111, 1.024 raised to the 18. And I'll need a calculator to do this. So I take out my calculator, and I do 7.111 times 1.024. And I raise that to the 18. And I hit enter, and I get out this answer here, and I'm going to round this to 3 decimal places, so that's a 5, so that's going to become an 8. So this will be approximately 10.898 and then million students. And again, this comes right from my calculator when I plug it in. And so 10.89, and then it'll become an 8 because there's a 5 here, so we round up. And then make sure you write down the units. So this is million students are enrolled in college in 1983. All right, that was an input question. And so typically following an input question comes an output question. So in what year will the enrollment reach 25 million students? So instead of plugging in for t, you're basically going to plug this in for this whole thing, E of t, which is the output. So we have 25 equal to, and on the right-hand side, you have the formula, 1.024 to the t. And this one's a little bit harder to do. And so we're going to need a calculator to do this. So the idea is we're going to graph the right and graph the left and then intersect. So take out your calculator, hit y equals. Let's clear out anything that's in there. And we just come up here and we put in the formula. So 7.111 times 1.024 raised to, now here you don't have a t button, so you just use the x. That's your input variable. And then here you're going to put 25. So you put the formula in the first line and 25 in the second. You have to make your window. So here's where you have to think a little bit. So think about how the years work. They start at 0 in 1965, and we want to go into the future. If you look at the table, you'll notice that after 40 years, you only have about 17.5 million. So we want 25. So we're going to have to go pretty far in the future. So maybe I'll put 100 years here, and then I'll go to zoom and go find zoom fit. Right, so you don't have to change the outputs, because if you just hit zoom fit will fit the output to the input. And you hit enter, and so there's a graph of our formula, which is really an exponential function. We'll talk about that later. And there's a constant, a horizontal line, and you see that they intersect right here. So I typically like to draw something so I can show some work in case I do something wrong. I can get some partial credit. So 0 to 100, and it went up like this and across like this, and I tell everybody, hey, I'm going to do this intersect button on my calculator, so I just usually write intersect and put a box around it. And then I take out my calculator, I hit second, trace, and then I go down to number 5, which is intersect, so I just hit number 5, and then it walks you, it kind of walks you through it, right? So it asks some questions like first curve, yeah, that's a first curve. Is that the second curve? Notice they put the curves on top here, so y2 is 25. Yeah, that's the second curve. Guess there's only one intersection point, so you just hit enter, and it'll jump right to it. So t is about 53 years. So remember, we're using t, but there says x here because our calculator only has input versus output. So it says when the enrollment is 25 million, basically your input, your t value will be 53. So over here, let's write t is about 53. And then I can add that to 1965. And so you can do that on your calculator. When you do that, you're going to get 2018. So that's the year that I would expect the enrollment to hit 25 million. Okay, let's look at the next problem. So the next problem, we're going to start talking about functions now, and what is a function and what is not a function. And here it says, give an example of a table and a graph that do not represent a function, and try to explain a little bit why. So let's do the table first. And so remember the idea of a function. A function is simply a rule that that assigns basically to each input value a single output value. And so what we need to do to have not a function is we need to have some input and some output. And when we plug in an input value, we can't get out just a single output value. So let's just do an example. So like suppose I plugged in 1 to my function and I got out, let's say 8. And then let's plug in 1 and then get out a different number, and this will violate the single property, okay? So it's like, if I plug in 1, I get an 8. If I plug in 1, I get a 9. Now it's not a function. It doesn't matter if 2 goes to 8 too. What matters is that 1 went to 8 and 1 also went to 9. So it's no longer a function because 1 has to go to a single output. All right, so down here, if we want to explain this, we can say not a function. Well, let's use a complete sentence. Why not? This does not represent a function because 1 goes to 8. So let's just write 1 arrow means goes to 8, and 1 also goes to 9. All right, so remember the idea of a function, each input goes to a single output. And if it goes to more than one output, then you're in trouble. So that's not a function. And then let's do a graph. So for a graph, we draw two axes, an x and a y. And probably the simplest one is just a circle. That's a nice example of a graph that is not a function. There's several ways to explain this, but again, you can see, right? This does not represent a function. Why? Because if you look at the input value of 0, so here's 0 right here, it's going to go, and let's put some numbers up here. Let's make this 1, and let's make this -1. So you can see that 0 goes to 1, and 0 goes to -1, because above it, there's a point on the graph at height 1, and below it, there's a point on the graph at -1. All right, so again, you can say this does not represent a function because 0 goes to 1 and 0 goes to -1. We also sometimes use what's called the vertical line test for this one. So the vertical line test says if it hits it more than once, then it's not a function. So it does not pass the vertical line test. Now you may have noticed I almost said horizontal line test because there is a horizontal line test too, but that tests whether a function has an inverse or not, and we'll talk about that a little bit later. So the vertical line test is used on a graph to see if a function, to see if a graph is actually a function. But again, it's very easy. You just look at the input and see if there's more than one output above or below it. If there is more than one, then it can't be a function. Okay, let's look at the next problem. So on number 3, we finally get to this graphing problem. And so I need to, I'm going to zoom out just a little bit here, like that. Okay, so on this one, we want to go through this and do the domain and range. So remember, the domain is input, and the idea is you look along the x-axis here, and what you'll notice is that you always have a graph above and below. And so the domain is everything. So this would be from -infinity to infinity. So we'll always use interval notation to represent this. So this says you can put whatever you want in there, and then the range are the outputs. Now, notice below here, below -3, there's nothing. Okay, so if you try to go to the left or right, you'll see there's no graph. So it starts right here at -3, and I'm going to include it because there's a closed circle here, and it's always implied that there's a closed circle here with a graph. And so then you look to the left or right, and you'll see there's a graph, and it goes all the way up. So it's everything. You keep on going, you keep on going. And so this one, the range would start at -3, so we would include it, and then it goes to positive infinity. Okay, this is the only time when you may use closed brackets. For all the rest of these, like increasing, decreasing, concave up, and concave down, they'll always be open parentheses. Okay, so let's look at some x-intercepts. So x-intercepts are where you cross the x-axis. So right here is an x-intercept. Right here is an x-intercept. So this is the point 0, 0. So that's the point right there, 0, 0. And then this is the point. It always goes input, output, remember, so it's 4, 0. So there's 2 x-intercepts, one at 0, 0, and one at 4, 0. And there's one y-intercept, if you notice. There's one y-intercept right here. So it has a common x-intercept and y-intercept, and it's at 0, 0. So that's how you find intercepts. You just look at where it crosses the x-axis versus where it crosses the y-axis. Let's erase some of this stuff so we can do increasing and decreasing. So for increasing, you want to see where the function's going up. So here it's going down, and then right here it starts to go up. So I'm just going to trace it the best I can on here with green, and it continues to go up. And then it's going down over here. So again, you always read a graph from left to right. And so it's going down, it continues to go down and down and down right there. And then when you write this down, remember, you're going to use interval notation. So it's increasing, so it starts here at 3 and then goes all the way out to the right. So increasing from 3 to infinity, so you tell me the inputs. So on these input values, if you look on the graph, you'll see you're increasing, versus it's decreasing, then all the way here until you get up to 3. So I would say -infinity to 3. Now, some people may argue that at this single point right here, it's leveling off. So we don't want to count that as decreasing. So, you might write something like negative infinity to 0. So that's from here to there. And then union 0 to 3, which would also be fine. So either one of these is a fine answer for this class. Relative maximum and relative minimum, that's basically where you change color. So let's just look right here. When you go from red to green, you change color, you have obviously a relative minima. So here I'd say I like to give input and output. You have to at least give the output. So f of 3 is the input. So this is the input. And f of 3, that's the output, which is equal to negative 3. And then from a maxima, you have none. Right? There's no relative maximum, and of course it goes up on each side, so it doesn't stop there. All right, let's do concave up and concave down. And so we'll recolor this now. And so for concave up, it's like a smile, so I'm going to use green. And so you see it's really smiling here. That's a nice part of a smile. And then it turns into a frown, so now it's concave down, so we'll use red for that. So it goes from green to red here. And then it goes back to a smile, so we'll switch back to green. And this is all part of a smile. And it continues to smile all the way, forever and ever on the right. So it's concave up where? So let's shade in the region on the number line up to 0. And then we pick it up at 2 when we're concave up all the way to the right. So here I would just write down negative infinity to 0, union 2 to infinity. And then it's concave down in between. Right, so this is where it's concave up, and it's concave down in between 0 and 2. And then finally, you get these inflection points. Remember, an inflection point is where you change concavity. So you go from concave up to concave down, or you could just say, if you color it, you change color, and then you go from concave down to concave up. So there are 2 inflection points. One happens at 0, 0, and the other occurs at the point 2, negative 2. So remember, when you're writing interval notation versus when you're writing points, we do use the same notation, but they mean completely different things. And from the context, we're supposed to figure this out, right? So from increasing, decreasing, or concave up or concave down, these are all intervals. Whereas for x-intercepts and inflection points, these are actually points. The same thing could be said for words. It's like, I go to school, or look at my eye. Right? They sound the same. Of course, we spell them different, but they sound exactly the same. But from the context, I go to school means myself going to school, whereas, look at my eye means, look at my eyeball, basically, right? So from the context, we should be able to tell whether it's a point or an interval. All right, so let's wipe this. We have a few more questions that we need to do below this. So let me scroll down a little bit. And so below here, it says find the x values. So find the x values where f of x is this. So this is, remember, greater than or equal to, because it doesn't look like an L. So basically what this is saying is this is output stuff. So when is the output bigger than or equal to 0? Or when is the output positive or 0? So you look up here, and the output above the x-axis is positive. So all this stuff going all the way up is positive. And then you want to include this because it's or equal to 0, and then over here it's equal to 0, and it goes all the way up. And so what I would say is you're going to give me the x values, so it's going to use interval notation, so all these x values up to 0, so include 0, and then include 4 and all the way to the right. So down here I would just write negative infinity to 0. It includes 0 because at 0 it's equal to 0, and then union include 4, because at the input value of 4, it's equal to 0, and then all the way to the right, so to infinity. Because over to the right, above it, the graph is positive. And so that's my answer for L. And then finally, we have a related rates, not related rates, I'm sorry. We have an average rate of change question. And so we want to find the average rate of change between x equal 2 and x equal 4. I'm going to redraw this question up here. So we're going to find the average rate change between x equal 2 and x equal 4. That way we can take a look at this picture. And you can write your work below that, of course. Okay, so on here, I'm going to erase this. And let's take a look at what happens when x is equal to 2. So when x is equal to 2, you're at this point. Whereas when x is equal to 4, you're at this point. And we want to calculate the average rate of change. So remember, the average rate of change is the change in the output over the change of the input. Or we could be a little bit fancy and write delta y over delta x, which really means the change in the output over the change in the input. And we should practice functional notation because this is a thing that students typically struggle with. And so when we're going from input 2 to 4, the idea is the output is f of, because this is the function of f of x. And so you have f of 4, it's always the final minus the initial, minus f of 2, divided by 4 minus 2, which equals, then we're going to read this off. So remember, this is the point 4 comma 0. So the output here is 0, so you have 0 minus. And this point, of course, is 2 comma negative 2, right? Input, output. So its output is negative 2. And then on the bottom, 4 minus 2, of course, is 2. And so this is equal to, you have 0 minus a minus, or minus a negative. So you have 0 plus 2. So that's actually 2 on top, divided by 2, which is equal to the number 1. Right, so the average rate of change is 1. Now remember, what does this actually represent? So it's telling you how the output is changing with respect to the input. So you'll learn, or we'll learn about lines here on the next exam. So basically what we're doing is if you connect the dots here, you get a line. And we're actually just computing the slope of that line. So on average, it's telling us, since the slope is positive, since the average rate of change is positive, on average, this function is going up between 2 and 4. And how is it going up? Well, if you go over 1 x unit, you go up 1 y unit. That's basically what it's saying, because the average rate of change here is 1. So you can actually think of this as 1 y unit per, so divided by an x unit. So if you go over 1 x unit, you go up 1 y unit on average on this graph between 2 and 4. Okay, that's enough of that. Let's take a look at the next question now. So the next question involves this idea of difference quotient. And this can be a bit tricky, so you want to try to follow along the best you can. And so here's the difference quotient. We don't need to memorize it. It'll always be given to us. So f of x plus h minus f of x, all divided by h. And then here's the formula right here. Now the tricky part is the f of x plus h. So let me do the part that you guys typically are pretty good with. So the h is in the bottom, that's no problem. And then over here you have minus f of x. The only thing you guys struggle with here is when you minus f of x, make sure you put parentheses around it. So it's minus x squared minus 2x plus 3. And then end parenthesis. And now what we want to do is we want to plug in x plus h in for x. So remember, f is simply a rule. It's a rule that, whatever is here, you put here, and you put there. So if this is what's here now, we're just going to do it. Right? So whatever it is, you square it, take away 2 times it, and add 3. So that's our new it. So we're going to square it. So x plus h, quantity squared. We're going to take away 2 times it, so 2 times x plus h. And notice you have to put parentheses around it. If you just put 2x plus h, then you're not multiplying it by it. You're just multiplying the 2 by the x. So you have to put parentheses. This is 2 times it. And then, of course, plus the 3. So that's how you figure out f of x plus h. And now you have to do some additional work. You have to square that out. So let's square this out on the side to kind of review things. So if you do x plus h quantity squared, that's x plus h times x plus h. And it's just a simple FOIL operation, or just use these arrows. So this times this, and this times that. So you're going to get x squared plus xh. And then this times this, plus this times that. So you get plus hx plus h squared. And of course, the two middle terms are the same. And so that's x squared plus 2xh plus h squared. And so down here, I'm just going to replace this with what it's equal to. So x squared plus 2xh plus h squared minus, I'll distribute this minus 2 through, so minus 2x. And then, so it goes here, and it goes there, so then minus 2h, and then plus 3. And these parentheses are so important because you guys tend to drop them off, but then you forget to distribute that minus sign through correctly, so it's minus x squared. But then a minus is a plus 2x, and a minus a plus is a minus 3. And this is all divided by h. And then you're going to see a lot of things are going to cancel. So like the x squareds will cancel because you have plus and minus. The minus 2x will cancel with the plus 2x, and the plus 3 will cancel with the minus 3. And so what we have left over is a 2xh plus h squared, and then a minus 2h, and then that's all divided by h. And we're almost done. So now what we need to do is we need to somehow figure out how these h's cancel, because that's really the end game. When those h's cancel, we're basically done. And the way this works is you see that they all have an h in common. And so what we can do is we can factor out that h. So h times something plus something else minus something else, and then all divided by h. So I kind of set this up, and then I just simply ask myself the question, what goes here times h is 2xh. And if you listen to the words, it'll tell you, oh, it's 2x, because 2xh is 2xh. And then what goes here times h is h squared. Oh, you need an extra h, because h times h is h squared, minus what goes here times h is 2h. Again, listen to the words, a 2. So 2h is 2h. And then you can see that the h's cancel, and we're left with our final answer, 2x plus h minus 2. So remember, at the end of the day, this difference quotient, what it actually helps us do, it helps us measure basically increasing and decreasing, concave up and concave down. But you won't actually use it until you get to calculus 1. So let's move on to the next problem. All right. So the next problem, what do we have? All right. So we have this sort of algebra of functions. So make sure you understand how the review is sort of laid out. So we start with sort of mathematical modeling as sort of a reason as to why we study functions, because it can be used to model real life things. And then we get into sort of more the abstract theory of functions. So you have, finite, increasing, decreasing, concave up, concave down, inflection points, maxes and mins, and things like that. And then using this average rate of change to sort of figure out, if it's increasing or decreasing. And then this idea of the difference quotient, which is connected to this sort of idea of average rate of change. And then we get into sort of the algebra of functions. And so in the algebra of functions, we can add, subtract, multiply, divide, and compose. And so that's what the meaning of this type of problem and the one that follows after it. So let's go through this. And let's just do it. Okay, so here, what do we have? We have f of x is equal to 2 minus x divided by x plus 3, and we have g of x equals 2x minus 5, and we want to do this, f composed with g of x, and then find its domain. Okay, we haven't done a domain problem with a formula yet. All right, so the first step is just to copy down f composed with g of x. So this is just a bunch of symbols, and we need to translate it. So what does this mean to do? So this means, basically, do f of g of x. So that's what it means. It keeps the same order, so it's typically pretty easy to figure out. So it's f of something, and the something is the g of x. So this is g of x, 2x minus 5. So wherever you see g of x, you just replace it with 2x minus 5, because that's what g of x is equal to. And now it's a new problem. What is f of 2x minus 5? So then you have to go over here to f, which is right here. And now what is f? F is simply a rule. Whatever's here, you take 2 minus it, and then divide by it plus 3. So now this is your new it. So whatever it is, you're going to do 2 minus it divided by it plus 3. So I'll have 2 minus, right, whatever it is, and it plus 3. Right? And it, I'll do this in different colors. It is just this thing. So 2 minus, and then in parentheses, because you subtract off the whole thing, 2x minus 5. And then here, you could, if you want to put parentheses again, you can, 2x minus 5, but you don't actually need to because you're adding. But that's the idea. So whenever you see these things, you replace it with this thing. And I always like to kind of say it, then do it. So f of it is 2 minus it, all divided by it plus 3. So 2 minus it, all divided by it plus 3. And then I need to simplify, so the rest of this is just algebra. And so here I have 2 minus a 2x. And again, the parentheses are important, otherwise you guys typically forget to distribute that minus sign through correctly. So minus a minus is a plus 5. And on the bottom, you really didn't need the parentheses because you're adding, so you just get 2x minus 5 plus 3. And then the numbers you can combine, so you have 2 plus 5, which is really a 7. So we have 7 minus 2x. Divided by, and on the bottom you have minus 5 plus 3, so that's 2x minus 2. And so that's our answer for this problem. And then to find its domain, so here's the formula. And so remember, there are two things right now that might limit our domain. So let's think about this. So for our domain, there are two things that limit our domain. One, you can't divide by 0, so this is how I think about it. Can't divide by 0. I'll put it in quotes because it's really me thinking. And then 2, if you have an even root, but in particular we deal mostly with square roots, make sure whatever's inside there is bigger than or equal to 0. Because if you get something that's negative inside of a square root, then we have to work with those imaginary numbers or complex numbers. All right, so now we don't have any square roots, so we don't have to worry about that, but we do have a denominator. So to figure out my domain, I need to watch out for that thing being equal to 0. So I want to make sure that 2x minus 2 is not equal to 0. So I add 2 to both sides, and I get 2x equal to 2. And then I divide both sides by 2, right? And 2x not equal to 2, so then x is not equal to 1. So divide both sides by 2 and get x not equal to 1. So that's what I want x not to be. And of course, when we write down our domain, we want to make sure we put it in interval form. So here's 1. I'm going to take it out. So it's everything except for 1. So let's shade in everything except for 1. And so the domain's really easy to write down. So d is equal to, all the way to the left, so that's negative infinity, to 1, in parentheses, union 1 to infinity. And that's my domain, everything except for 1. All right, so moving on to the next problem. What do we have? Okay, so in this problem, we're going to work with a table, a graph, and a formula. And again, we're doing the algebra of functions, so we want to, how do we add, subtract, multiply, divide, and compose? So let's go through each of these, and basically the first step is just translating what this says. So if you have g plus h of negative 2, what that really means is do g of negative 2 plus h of negative 2. And then we're going to use the tables and the graphs and the formula to figure these out. So this will be equal to g of negative 2, so here's g. And then you go negative 2, so negative 1, negative 2, so this is the height, which is no height, so this is 0. Plus, then h of negative 2, now you have a formula, so wherever you see an x, you're going to put a negative 2. So you have 3 times negative 2 divided by 5 times negative 2, and then minus 4. And so that's going to be equal to negative 6 on top, so it's 3 times negative 2 is negative 6, and then 5 times negative 2 is negative 10 minus 4, and that's equal to negative 6 divided by negative 14. Of course, the negatives cancel, and they're both even, so the 2's cancel, and you get 3 over 7. All right, and then the next one, what do we have? So we have f minus g of negative 3, so that's equal to f of negative 3 minus g of negative 3, which is equal to, now f of negative 3, we go over to the table because that's f, and if you plug in negative 3, you get out the number 2, so that's 2 minus, and then when you plug in negative 3 to g, so that's negative 1, negative 2, negative 3, you're right here, which is height negative 1. So minus a negative 1, which is equal to 2 plus 1, because a minus and negative is a positive, and that's equal to the number 3. And then down here, this one's equal to, we have f times g of 0, so that's really f of 0 times g of 0, which equals, so f of 0, well here's 0, if you plug in 0 you get out negative 1, so it's negative 1, times, and then g of 0, well here's 0, you plug it in, you get this point up here, which is height 2, and that's equal to negative 2. And then we come back over here to the right, and we have h divided by g of 1, so that's really h of 1 divided by g of 1, and that's equal to, so now again, you're working with a formula, so to find h of 1, wherever you see an x, you're going to plug in a 1, and so we have 3 times 1 divided by 5 times 1 minus 4, so that's on top, h of 1, and then on the bottom, we have g of 1, so if you plug in 1 into g, what happens? Well, you got to be careful because this is an open circle, so we're not at this height, we're up here at this closed circle. And so you go over 1 and go up 1, 2, 3, so this is equal to 3. And then on top we need to simplify, so we have 3 divided by 5 minus 4 is 1, and that's all divided by 3. And so 3 divided by 1 is 3, so 3 over 3 is equal to 1. And so that's my answer for that one. And then we come down here, we're going to do some composition. So for composition, we have h composed with g of negative 2, so that's really h of, let's do this in a different color, g of negative 2, so g of negative 2. And so first we need to find g of negative 2, so if you plug in negative 2, go negative 1, negative 2, you get this height right here, which is height 0, so this is equal to h of 0. And then we go and plug in 0 in for x over here because it's h of 0. And so you're going to get 3 times 0 over 5 times 0 minus 4. And so on top you have a 0, and on the bottom we have negative 4. But 0 divided by any number is just simply equal to the number 0. So 0 is my answer. And then on this one, we have h composed with f inverse of 3. So that's h of, and on the inside, let's put f inverse of 3. So h of f inverse of 3. So that's what this says. And that's equal to h of, and f inverse of 3. So now remember f inverse, instead of going from left to right, you go right to left in a table. So here's my table. So instead of going down this column, since f inverse, I go down this column, you see there's a 3 there, so f inverse of 3 is just equal to the number 1. So you go back the other way for f inverse. And so that's h of 1. And then you come over here and you plug in 1 because it's h of, so you come in here and plug in 1 for x. So wherever you see an x, you put a 1. And you get 3 times 1 divided by 5 times 1 minus 4 on the bottom. And so that's 3 on top, and then divided by 1 is just the number 3. All right, let's scroll down a little bit, and this one says find h inverse of x. So up here, here's h of x. Let's rewrite it down here. Instead of writing h, I'm going to write y. So y equals, and I copy this down, so it's 3x all divided by 5x minus 4. And to find the inverse from a formula, it's actually very simple. Right, all you need to do is swap out the y and the x. So let's do that. So wherever I see a y, I'll write an x. So I have x equals, and then I have 3y divided by 5x minus 4. Oops, I forgot to write that y there. Okay, so here, let's erase this actually. And I need to write a y. So this is 3y minus 4. And I want to solve this for y now. And so first thing I need to do is clear denominators. So the way you clear denominators is I have a denominator here, so I'm just going to multiply everything by 3y minus 4. And so this will be multiplied by that. This will be multiplied by that. So on the left-hand side, you'll have x times 3y minus 4. And on the right-hand side, it's nice because these are going to cancel. So 3y minus 4 on bottom cancels with 3y minus 4 on top, and you're left with just 3y. Right. Now I'm going to multiply through by the x. So I'll multiply this by x and this by x. And so on the left, I'll get 3xy minus a 4x is equal to a 3y. And I want to get all the y stuff to one side, so I'll take away 3xy on both sides. And I'll get a negative 4x on the left. And on the right, I'll have 3y minus 3xy. And then what I can do is I can factor out, oh, I just saw I made a mistake here. So let me go back and fix this. I copied this down wrong. This is supposed to be a 5. So fix that. This is supposed to be a 5. That means this is a 5. That means this is a 5. And this is a 5. So let's take that away from each side. So maybe you saw that. If not, fix it in yours. That's supposed to be a 5. I copied the problem down wrong right here. Okay, so now we're on this step. And remember, we're trying to solve for y. So what you want to realize is that these have a y in common. So you can factor it out. So what we have is negative 4x equal to, we'll pull out a y, and then something minus something. And there's a 3 here and a minus 5x there. Right? So this times this is that, and this times this is that. And then finally, we can solve this for y by dividing both sides by 3 minus 5x. So on the left-hand side, we get negative 4x over 3 minus 5x is equal to y. And that is a fine answer. You can leave it like this. You could also rewrite this. Instead of writing y, you could write h inverse of x equal to negative 4x over 3 minus 5x. That's also a good answer. And remember, you can check your work. So on these problems with inverses, you can check your work by plugging in a number. Like suppose you plugged in h of 1. So h of 1 would be 3 times 1 over 5 times 1 minus 4, which would basically equal the number 3, because you have 3 divided by 1. And then to check your work, you can plug into h inverse. So h inverse of 3. Now if it's the inverse, if you plug in 3 to the inverse, you should get back the number 1. So you can check it here. You have negative 4 times 3 divided by 3 minus 5 times 3, which equals a negative 12 over 3 minus 15 is also a negative 12. Oh, and that is equal to positive 1. So 1 goes to 3, 3 goes back to 1. So check. That's definitely the inverse. Okay, next problem. So on to transformations now. So for transformations, remember we have all these different types of transformations. So you have a shift to the left, to the right, up or down, basically vertical shifts or horizontal shifts. You have horizontal stretches or shrinks, or vertical stretches or shrinks. And what we want to do here is consider this function, which you should know the graph of. And we want to use transformations to graph this function and describe each transformation in the process. So let's start with our graph here. So here's the graph of f of x equal to x squared. And it's just a nice looking parabola. It looks like this. And what we want to do is transform this into that by performing a sequence of transformations. And so what you have to ask yourself is, how is this function different from this function here? So how are these two different? Well, this one has a plus 1 times a negative 3 and then a plus 5. And what's the order in which these transformations occur? Right, so remember, you can always plug in a number like 6 here. And if you plug in 6 here, then the 6 goes right here. And you say, okay, what do you do first to the 6? Would you add 1? Would you take it times negative 3, or would you plus 5? And of course, you would add 1 to it. So the first transformation is add 1 to the input. And the next transformation is take it times negative 3 to the output, and then add 5 to the output. So that's kind of how I decide on the order of the transformations. All right, so let's do this. So the first transformation is basically, in some sense, you're adding 1 on the inside. So remember, when you do the thing on the inside, you do the opposite. So this is a horizontal shift because it's on the inside. And I want to say to the right, but it's to the left. So this is a horizontal shift to the left 1 unit. So my resulting graph, when you shift this to the left 1 unit, it goes from here, and let's do this in a different color, let's do it in red. It goes from the origin to -1. And so we just copy the graph again. It's just shifted over right there. And then the next transformation, so we did the +1 on the inside. Now you have times -3 on the outside. So now when you take something times 3 on the outside, it's going to stretch it vertically by a factor of 3 because it's on the outside. But negative flips it over the x-axis. So what this is, on this transformation, it's actually two things in one. You're going to do a vertical, because it's on the outside, stretch by a factor of 3, factor of, all right, we're in there, so a factor of 3, and reflect it over the x-axis. That's what a negative sign does. Right, so that multiplying by 3 will stretch it by a factor of 3, but when you multiply it by a negative, it reflects this thing over the x-axis. It makes the positive stuff go negative. So let's draw this one down here. So let's go down a little bit. And let's make this better. Let's do it right here. Okay, so multiplying by a factor of 3 basically makes it more narrow, and then we're going to reflect it, so we're going to pull it over the x-axis. So you're still at -1, and it's just going to be down here, but more narrow. So let's just make it a little bit more narrow, because it's basically going to pull this up by a factor of 3, each of the heights, and then reflect it over the x-axis. And then finally, we have the +5, and +5 is a vertical shift up by 5 units. And so we can draw that right here. We're still at -1, and we're just going to move it up 5 units. So let's put 5 right here, and then we can draw it. Let's draw it in purple. So we'll put this at -1, 5 right here, and just shift it up 5 units. So it looks something like this. And so what we have here is a horizontal shift to the left by 1 unit. So that's the x plus 1 quantity squared. And then over here, we stretch this by a factor of 3 and reflect it over the x-axis. So that's the -3 times x plus 1 quantity squared. And then finally, we shift it up 5 units. And so that's the -3 times x plus 1 quantity squared, and then up by 5 units, so +5. And that's our graph of our g of x. So on number 8, we want to create a table, a graph, and a formula that represents a function with each property, and try to explain a little bit about why on each of these. So we want to create a function that has an inverse. So again, let me sort of outline these. We want to make a table, and then we want to make a graph, and they don't have to be the same function. They can be different functions. So then a graph, and then a formula of a function that has an inverse. So for f of x, what you need to do is make sure all the outputs are different. So it doesn't really matter what the inputs are. I mean, the inputs have to be different too, right? But it doesn't really matter. So let's do like -1, 0, 2, and 3. just for fun, and just make the outputs different. So if you're going to put a 5 here, you can't put a 5 again. So let's make this 5, 11, 7, and 8. And so this will have an inverse because if you give me the output, I'll tell you which input it exactly came from. And I mean, that's the idea. So, why does this have an inverse? Because each output, you can say each output comes from a unique input. Right? Or you could say each output comes from a single input. That's another way of saying that, 5 only go back to one thing. We can also do a graph. So for something that has an inverse, most lines have inverses. Right, so you can see that this line has an inverse. The idea is if you give me an output, right, so take any output you want, pick an output. So here's an output. You look on the graph, and there's the output there on the graph. It'll go back to a unique input on the bottom. Basically, we say, these things are 1 to 1. Right? So for each input, there's a unique output. And then for the function, well, since this is a line, any line will work. So you can just say h of x equal to x. That'll have an inverse. And again, because these things are all 1 to 1, so each output comes from a unique input. And then let's draw a function that does not have an inverse and try to explain why. And so this one's actually pretty easy too once you get the hang of it. So we'll do a table. So x, f of x. We'll do a graph, g of x. And then h of x over here, we'll do a formula. All right, so for a table, we can do the same. Let's do the same numbers just for fun. So -1, 0, 2, and 3. And what you need to do on the right is repeat a number. So let's make this 5, and let's make this 5. And these, I don't care what you make these. Let's make this 7 and -13. And so this function does not have an inverse. All right, so we can write this function does not have an inverse because why? Because -1 goes to 5 and 0 goes to 5. So it is not 1 to 1. Right? That's the big idea. So if I give you an output like 5, well, some of you might say it goes back to -1, but some might say it actually goes back to 0, and you're both right. So that's why it doesn't have an inverse, because we can't really decide, did 5 come from -1 or did 5 come from 0? And so that does not have an inverse. Here, a function that doesn't have an inverse is probably my favorite is this one, just a parabola. And again, you can see that if you give me an output, so here's an output value, you can see over here there's an output value on the graph, and here it has the same output value, and you can see it comes from not one input value, but from 2 different input values. So again, a single output value comes from 2 different input values. It can't be 1 to 1, so it does not have an inverse. And sometimes we talk about, in this case, instead of the vertical line test, we talk about the horizontal line test. So the horizontal line hits it more than once, and so it can't have an inverse. So it fails that horizontal line test. And then, of course, f of x equal to, if you're doing a parabola, you might as well just do x squared. And again, this doesn't have an inverse because if you look at f of 1, it's equal to 1, and so is f of -1. -1 quantity squared is equal to 1. So if you ask what input gave you the output of 1, you'd say, some people might say 1, but some people might say -1. Right? So this output comes from 2 different inputs. So again, it's not 1 to 1. Right, let's take a look down here at these last two. So this has to do with symmetry, and we want to talk about being even. versus being odd. And so let's look at a function here, xy, and then we'll do a table here, and a graph here. So we'll do a table, and then we'll do a graph, and then we'll do a formula, h of x. So I should label this g of x, let's say. We'll go along with what we've been doing, and we'll label this f of x. And then we'll do the same thing below it, but instead of an even, we'll do an odd. So let's just kind of compare and contrast these all at the same time. So you have x and y. We'll make another function. We'll call it g of x down here. We'll make another function. We'll call it f of x down here. So for an even, right? So remember the idea of an even function. The idea of an even function is your outputs on either side are exactly the same. So what you need to put in here are some negative numbers, like let's say -2, and like -1, and then 0, and then also they're positive, so 1 and 2. So you can compare them. Same thing down here, but you can do different ones, right? So you can do -3, -1, 0, 1, and 3. You don't have to be in order to give an example. They don't need to be in order to give an example of an even or odd function. You just need the opposite, so then you can make a decision. So over here for even, if this is, let's say, 7, then this also has to be 7. And if this was -3, then this would also have to be -3. And then 0 can be whatever you want, so let's just make it 11. So this is an even function because when you plug in -2, you get out 7. And when you plug in +2, you get out 7. So they have the same value on opposite sides. So they satisfy this definition. The output on either side is the same. Whereas down here, when you plug in opposites, so let's make this -8. Then that means if you plug in the opposite, it has to be +8. Whereas if you make this one 7, this one has to be the opposite, which is -7. And then for an odd function, 0 is actually forced to be 0. So what happens, if you think about it, on opposite sides of the y-axis, these aren't exactly equal, they're just opposites of each other. So -8 on the other side is +8. 7 on the other side is -7. And at 0, it has to be 0 because the only number whose negative is itself is 0. So 0 is equal to -0, negative of -0. It's the only number whose negative of itself is itself again. All right, so let me rewrite that. So 0 is equal to -0. That's what I want to write. And then for a graph, okay, so for an even function, I could pull out my old friend, the parabola. That's a great example of an even function. Or you could do the absolute value function, which is a v. And again, you can see, why is this the case? Well, the output over here is the same as the output over here. So again, it satisfies this definition. The output on either side is exactly the same. And then if we're going to do a parabola over here, we might as well do x cubed over here. So x cubed looks like this. And these are supposed to be the same on either side, but opposites of each other. And so you can kind of see the idea is that if you take a value over here, you get out a height. You take the value over here, you're supposed to get out the same exact height. So g of x isn't exactly equal to g of -x. It's the opposite. So here I equals -it. And then finally for the function, right, since we used the parabola, let's just use x squared. And you can see even function, even power, odd function, odd power. So these are easy sort of to remember. And again, you can go through the definition and say, okay, well, what does h of -x look like? Well, that would be -x quantity squared. Well, everybody knows if you square negative, it goes away. So this is just equal to x squared, which is equal to h of x. Oh, so look, h of -x is the same as h of x. So of course it's even. Whereas down here, if you look at negative h of -x, what do we have? Negative of -x quantity cubed. Right? So remember, h of -x, wherever I see an x, I put a -x inside there. So I have -x quantity cubed. And everybody knows a negative times a negative times a negative is a negative. So that's really negative x cubed. So notice the cube is no longer around the whole thing here. It's just around the x. And a negative is a positive, so you get x cubed back, which is your original function, h of x. Oh, so yes, negative h of -x is h of x. So of course it's an odd function. It satisfies the definition. So remember the definition here is f of x and f of negative x are not the same, they're the opposite on each side. And they don't get stuck on the f, right? It could be g, it could be h. It's just saying on either side, they're not the same, they're the opposite of each other, whereas for an even function, they're exactly the same. And so this completes the review.